Good. So let's start then. So it's a pleasure to introduce Tong Yang in the last session of our meeting this week, and Tong is going to give us a talk about analysis on the Orr-Sommerfeld equations for magnetohydrodynamics and CNS. Okay, please.
Yeah, thank you. So thanks, Jose, for the introduction. So my great pleasure to give a talk in this conference workshop. It's a pity that I cannot go to UK this time. So in fact, the topic I am talking about today is a bit far from kinetic theory and not much kinetic component. But at the end of the talk, I will mention some possible future work that is related to the Boltzmann equation. So I slightly changed the title of my talk. I add the CNS in addition to the MHD. Okay. So this is about some recent work with two of my collaborators. One is Chen-Jie Liu and another one is Zhang Zhu. Okay. So the purpose of this research, in fact, is to try to derive and analyze some OS systems, okay, derived from different fluid dynamical systems, such like the MHD or the compressible Navier-Stokes equation. And we all know that the classical OS equation is derived from the incompressible Navier-Stokes equation. So, so for some complicated systems, also for the compressible case, how to derive some similar equations or systems so that we can study the stability or instability phenomena. So this is the goal. Okay. So my talk consists of 3 parts. So in the first part, I will look at the simplest case. Simplest case in the sense that the format is simple. Okay. So you can derive an equation that is similar to the OS equation for INS, but how to analyze it is still not completely known. Okay, so this is the case when the MHD without a magnetic field, and then I will look at the MHD in the Harman-Penton regime and to derive another system to study the Thormeer shielding and instability. So in this topic, I will emphasize that there's a new decomposition in order to solve the OS system. Okay, so so the last part of my talk will be about the I will talk about the compressible NS, and then in that case, there will be another decomposition, so that that leads to the solvability of the OS equation. Okay, so so this is the talk, and then this is the overview I just mentioned. So now let me first recall the basic OS equation of, well, at least most of your audience know about it very well. So for the 2D incompressible Navier-Stokes equation, so if we linearize this system around a background flow, which is a shear flow, the 2D, so the tangential component depends on the normal coordinate. The normal component is 0. Okay, so if you linearize this system around this profile, okay, and then you look for the solution in this form, in the Fourier mode in X, okay, and the function of Y. This phi corresponds to the string function because it's in 2D. So plug this into the linearized system, one can obtain this famous OS equation. Okay, so this OS equation is a 4th order ODE. So it's the Vernet equation past this Laplace term, but it's a fourth order derivative now on the stream function. So epsilon is a small parameter. Okay, so it can be viewed as a singular perturbation of the Rayleigh equation for the inviscid flow. So there are a lot of studies and progress, important work on this equation. Okay, since it was derived more than 100 years ago. So here I among all those works I mentioned the work by two groups. One is Grenier, Yan-Guo, and Yan. Okay, started from 2015, and then in particular in their paper published in Duke 2016, they give the precise description of this, the eigenvalue and eigenfunctions to this OS equation. There's an elegant decomposition called the area Rayleigh decomposition, and then iteration scheme to solve the OS equation with, for example, Navier boundary condition. So a lot of estimates were given there, and then it's very interesting. So it gives, if in short, so it gives the instability estimate that corresponds to the Dirac index equals to 302. Okay. So in fact, this instability result was complemented by Gerhard Rayleigh, Maekawa, and Masmoudi in 2 years later, where they showed the Dirac stability for the 2D Prandtl expansion for incompressible Navier-Stokes equation in the function space Dirac to free half. Okay, so this Dirac free half is optimum. Okay, for this case, because you have instability and stability. Okay, so so our research, our program in fact is to see how to study the similar phenomena for other systems. Okay, so here I mentioned two systems. One is MHD, the other one is the compressible NS. Okay, so for the MHD, we all know that the equation is in this form. So we have two vector fields, vector functions, U and H, velocity and magnetic and divergence free. And here there are three physical parameters, Reynolds number, magnetic Reynolds number, and the coupling parameter, which is hard number square over the product of these two Reynolds numbers. Okay, so it depends on the ratio of these parameters. So there are different regimes and corresponds to the different stability phenomena. So in the first part, I would like to look at the so-called simplest case. Okay, so that's the when the Reynolds number is very large, so it's behaved like 1 over epsilon, and the magnetic Reynolds number is infinity. So the coupling parameter here I chose to be 1. Okay, just O1 constant. So in this regime, the MHD equation, if I write it out, is like this. So UV are the two velocity component, HG are the magnetic components. Okay, so there's no magnetic resistivity. So this, the right-hand side here is 0. Okay, divergence free. So we look at the background flow, which consists of the, for example, the ideal MHD solution and the boundary layer profile. Okay, so it has a strong layer, so it depends on the fast variable y over square root of epsilon. Okay, so if one linearize this system around such a background shear flow, then this is the linearized equation. Okay, also for equation plus divergence free, and then we look for the solution. Okay, so this is the standard with scale variable. Okay, so because we have fast variable y over square epsilon, so to have a better form in the final equation, so one also rescale the time and the tangential coordinate x. Okay, so under this new coordinate, we write the system is in this form, and then we look for the like the OS idea, look for the solution in this eigenmode. Okay, so u VHG is e to this power, and then times these four quantities. Okay, so here it involves two stream functions. Phi is the stream function for velocity field, and psi is the stream function for the magnetic field. Okay, so yes, so if one plug these answers to this problem, the resolvent problem, then it end up with this OS system. Okay, so now because we have two stream functions, so the it's not like the incompressible NS, which is only one equation for the stream function. Here you have two equations. Okay, so why I said that this is the simplest case, because the second equation only gives us the relation between the two stream functions, psi and phi. Okay, so there's no derivative here. So in principle, you can solve this equation. You can rewrite this equation using phi to represent psi and pi into the first equation. Then you have the only one equation for phi. Okay, so if you do that, then you end up with only one equation like this. Okay, so this is the OS equation for the MHD in this setting. Okay, so the only difference between this OS equation and the classical OS equation is this AY. There's a function AY, which is h squared minus u minus c squared. Okay, you have this. This comes from the coupling between the magnetic field and the velocity field. Okay, so you can see that this in fact appears as a coefficient in the second order derivative. Okay, so if the real part of this this function, this is a complex function. If the real part of this function has a definite sign, okay, then you will give us some good properties, okay, in the estimate. So in physics, this means if the tangential magnetic field dominate the velocity, dominate the velocity, this is the tangential velocity. Okay, so if the magnetic field dominates, then you have a good sign, then you have a good estimate. Okay, so this AY in fact plays a very important role in the analysis, because here I skip all the calculations, okay, for the analysis. So for example, for the steady case, if there's no time t, then this AY is just h squared minus u squared. Okay, so it's a real function. So this is used in the stability analysis in this paper. Okay, so one can show for the static case, if you have the magnetic resistivity, then the system or the background profile in fact is stable in H1. Now back to this case. So if you look at this equation, what we can prove the following. Okay, so we can show that this linearized system is in fact is well posed in any derived function space. Okay, with arbitrary index gamma greater than 0. Okay, so this is different from the what I just mentioned on the incompressible NS by the two group. Okay, which shows that the critical derived index 3/2. Okay, because here there's an assumption that the tangential magnetic field dominates the velocity field. Okay, and of course here there's another assumption is the monotonicity of the velocity profile. Okay, so with this dominance, then you don't need the assumption on the velocity field. Okay, but this is only a linear statement. Okay, a statement for the linear system. So it's not known how to show this is true for the nonlinear system, because without the magnetic resistivity, it's difficult to control the HY, the tangential magnetic field, the derivative in the normal direction. Okay, so so the nonlinear system is not known, and also here we only look at the simplest case when AY, the real part is a good sign. Okay, so if H is not dominate, H does not dominate U, then because U is 0 at the boundary, okay, it's O1 at infinity. So if H is in between, then this AY change signs. Okay, so if AY change signs, then there may be some other kind of instability phenomena, and this is not known. Okay, so the form of this equation is simple, corresponding to the classical OS, but there's still many equations that we don't know how to answer. Okay, so the second system that I would like to talk about is the case in the Prandtl-Hartmann regime. Okay, so why this is interesting? So let's first recall the Thormeyer-Schwinting wave. Okay, so there's a lot of work on the Prandtl boundary layer, which is in the first region when the flow passes a boundary. Okay, so this is the Navier flow. So before the turbulence, there's a transition region. So here, if there's a small perturbation near the boundary, even closer to the boundary than the Prandtl answers, then the inviscid perturbation and the viscous resonance response will have resonance. Okay, so so you will have a growth. Okay, then this growth by nonlinearity will grow faster and then lead to turbulence. Okay, so this is the intuitive thinking of the TS wave. So for the TS wave, there's work by I mentioned the work by Guanlier, Yan Guo, and Yan. Okay, and also some improvement by Zhifei Zhang and his group, and so on. Okay, so so the what's new? Okay, in the following study is that we want to look at the case for the magnetic field for the MHD in this regime, Hartmann-Prandtl regime. So what this means is the following. Okay, so let me first recall the MHD system. I just wrote down. Okay, the same system, but now let's look at the parameters in different scaling. Okay, so if you take the Reynolds number to be very large, like 1/epsilon, and the Hartmann number and the magnetic Reynolds number, like the square root of this number. Okay, then you have this system. Okay, this is the MHD. So this MHD system has a solution. It's a solution. It's called the Hartmann layer. So for any two constants, U infinity and H infinity, if there's a constant normal magnetic field, okay, transverse to the boundary. Here I take it just 1, then this is the solution. Okay, so you can see that it is exponential decay to a constant U infinity and another constant H infinity for the velocity and the tangential magnetic field. Okay, so now if we linearize this MHD system around this layer, okay, around this layer, and we do the same thing. Okay, so we consider let phi to corresponds to the velocity field, the string function, and psi the magnetic field, and we look for solution in the same form like this, and we plug these answers to the linearized system, then this is the OS system in this setting. Okay, so now this is much more complicated if we need to spend a few seconds to look at it. Okay, so the phi and psi, in fact, strongly coupled. Okay, strongly coupled. But if we look at the case in the high frequency, means that alpha and C are small, as like some power, positive power of epsilon. Then the dominant components, the coupling, the dominant coupling term is the term I marked in blue color. Okay, is this one. Okay, so these two terms, in fact, they are the same. Okay, except the normal derivative. Okay, so if you still use the second equation to replace this blue term by the dy of this term, okay, then we can have this equation. Okay, so this equation looks even more term involved, okay, more complicated, but in fact it's simpler in the sense it's it has a structure closer to the classical OS. So first of all, you can see that the first term is the same, okay, and the second term is more or less the same. For the classical OS, this is US minus C, but here now we have C hat. C hat is nothing more but C plus 1 over n. Okay, 1 over n in fact corresponds to the damping effect of the Hartmann layer. Okay, so for the Hartmann bounded layer, we all know that there's a damping effect, and this corresponds to this term. Okay, but n is very large because we look at the high frequency case. So this effect is small. So this is this term is, you can view this term more or less like the term in the classical OS. Okay, so this is the coupling term, but it has a good factor, small factor, square root epsilon. So this is the term also appear in the classical OS. Okay, and this is the coupling term, also with a small factor, square root epsilon, and n is large. So this, even though here this term looks complicated, but the coefficient, the factor is small, also this one. Okay, and for the second equation, nothing we can do, so it have to be there. So this is the relation between the two string functions. Okay, but the first equation, more or less like the classical OS, except some higher order terms. Okay, so this is the equation we would like to solve. Okay, so now before showing how to solve this system, let me state the film. Okay, the film can be stated as follows. So if we let the USHS to be the background Hartmann boundary layer, so you can show that if alpha is like epsilon to the 1 order power 1 over 8 with a very big constant, capital A. Okay, so you have alpha looks like this. Then the linearized system indeed has a solution in the form we just chosen. Okay, and more important is that for this solution, the alpha times the imaginary part of this C, okay, is of the order of epsilon to the quarter. Okay, so this is important in the sense that if alpha times the imaginary part of C is positive, and epsilon to the 1/4, and then because the denominator we have square root epsilon, so here you have T over epsilon to the 1/4. That corresponds to the fast growth of the mode. Okay. So this result, this estimate is also true when alpha is like epsilon to the beta. Beta is in this interval. Okay, I will give some comments on this, but let's first focus on this clear-cut case epsilon to the 1/8. Okay, because this corresponds to the Dirac index 3/2. So why this corresponds to the Dirac index 3/2? Because if we write the eigenmole more precisely, like INX plus sigma t. So sigma t, I just mentioned, if alpha times imaginary part of C is epsilon to the 1/4, then the real part of sigma is positive. It's like n to this power. Okay, so when the power beta is 1/8, then this power is 2/3. That corresponds to the Dirac index 3/2. Okay, so this is the key part. Okay, so now before I show how to prove this theorem, let me give two remarks. The first remark is this result in this shows, if we look at the TS instability, it shows the transversal magnetic field can be negligible, okay, in the Pendle-Harman regime. Okay, so because you have the similar phenomena like the incompressible NS. Okay, and now if you look at other regime, for example, if all these three parameters are of the same order going to infinity, then the situation is different. So in this regime, in fact, one can show that the tangential magnetic field stabilizes the flow. Okay, so here you have Sobolev well pose. Okay, not Dirac. Okay, can be finite order regularity. And also in the Pendle-Shakef regime, when the Reynolds number and the Harman number of the same order going to infinity, magnetic Reynolds number is square root of it. Okay, then this one can also, in this regime, the flow is stable in Sobolev space. Okay, so this is very different. Okay, so now let me recall the beautiful structure observed by Grenier, Gore, and Yan. So this is the classical OS. Okay, so yes, you can view this as two parts: the singular perturbation of the Reynolds operator, and if you look at the first two terms, okay, because US, if US is monotone near the boundary, so near the boundary is just like a capital Y times a constant. Okay, so the first two terms in fact give you corresponds to the area operator. Okay, plus this multiplier operator, so it's a regular term. So in their work, so there's an iteration among this Rayleigh and area, and then show the solvability of this OS. Okay, now this beautiful idea may not be difficult to apply to the MHD, because MHD now we have two equations. Okay, and there are a lot of terms. Okay, many terms. So you don't see such a clear-cut structure. So how to do this? So the main ingredient of the proof is to introduce a new decomposition of this system. Okay, through this decomposition, we can handle the source term with either strong decay like exponential decay, or with differential structure. Okay, differential structure. And then so this is the key part I'd like to emphasize, and the other part is can be technical. Okay, so you can look at the L2, can absorb this factor, and then how to recover the no steep boundary condition. Then we need to use the Roush theorem. Okay, using the analyticity of the function on the boundary in C. So okay, so this is the approach. Okay, how to do it. So similar to the incompressible NS, so one can construct the inviscid mode, okay, by looking at the by looking at the Rayleigh equation. Okay, so this is the Rayleigh equation. You can construct a approximate solution to this equation up to the order alpha. Okay, alpha, keep in mind, alpha is epsilon to the 108, okay, power. So you can also check that this approximate solution on the boundary y equals to 0 has this property. Okay, the function itself and also the derivative. Okay, it's this. And then the viscous mode is the mode closer to the boundary. Okay, closer to the boundary. The Prandtl layer is square root epsilon. So the viscous mode happens like epsilon to the this power 5/8. Okay. So why this is true is can be calculated like this. So you assume there's a extra scaling delta, okay, small, okay. So you construct the fast mode, the stream function of these two stream function in this even faster variable, and plug this into the equation and look at the leading terms. You end up to this area equation. Okay. So here here we use the velocity field at the boundary is monotone. Okay, so it's just like this constant times y. Okay, basically. So you have this area equation, and all these constants can be precisely calculated. So you can see that the fast mode is just the primitive, the second primitive of the area solution, and for the magnetic field is the third primitive function of the area function. Okay, so you normalize it, and then in order to satisfy this boundary condition. Okay. So the interaction of these two modes is just a linear combination. So here we want to at least satisfy this boundary condition. Okay, at the boundary it is 0. So how to do it? Because of we all know the boundary property of this slow mode and fast mode. You can do this linear combination. And so far we haven't defined the slow mode for the magnetic field. Okay, so the slow mode for the magnetic field can be solved by using the second equation. Okay, like this. Okay, so that this approximate solution satisfies these two conditions, but not yet the no slip boundary condition. So in order to recover the low slip boundary condition, we need to use the rough film. Okay, I will mention it later. So let me summarize a little bit. So far we construct two the stream function, approximate stream functions, right? And then this two stream function, if we plug it to the OS system, then it is not a solution. It has error. Okay, but this error has special structures. You can check. So this error either have derivative, either as like a derivative of a function. And I alpha is just the derivative in x. Okay, so either has derivative structure or exponential decay. Okay, so E3 is exponential decay, like e to the capital Y, the constant. Okay, and moreover, if you calculate in more detail, then you can see that you have this estimate on the error terms. Okay, it's epsilon to all this positive power. Okay, so now we want to show that there at least one approximate solution satisfies the low slip boundary condition. Okay, so we look at the C range in this disk. So this center is C star, is this number. I will show you why this number appear. Okay, it's just a number at this moment. And then we look at the disk with this center and the radius a to -1 minus theta. Theta is a positive parameter to the epsilon to 1/8. Okay, so A is capital A is very small. So because A is very large, so you can see that this disk is closer to the real axis, so it's far from the imaginary axis. On the other hand, because it is epsilon to the positive power, so it's very close to the origin. So here I exaggerate a little bit. Okay. So now, if we look at the dy phi, okay, which is u on the boundary, we want to show that there exists a c. It is 0. Okay, so we need to calculate this part. Okay, so how to do it? So we can first estimate the leading term of this right-hand side, and by doing this, so because every term has a scale epsilon to the 1/8, so you can the scale as a O1 parameter h. Okay, so if you look at the leading term, which is this one for in terms of h, so you want this to be 0, that is the leading term, right? If this is 0, this is exactly corresponds to the C star. H star is the C star, because up to the epsilon over A factor and this shift. Then for this reference gamma hat, we have 0, okay, at H star. Then along the circle, you can show that this gamma hat, in fact, is of the order of A to this power, okay? But the difference of these two gamma is smaller, okay, less than 1/2 of this quantity. So all the functions are analytic. So by Roche theorem, you have the H approximate, so that the original gamma is 0. Okay, so this shows that the approximate solution indeed is satisfies the low-slip boundary condition. Okay, let's go fast. So now with this approximate solution, then we need to solve the remainder term. Okay, so let me first recall the classical OS. So this is the classical OS. Okay, classical OS, in fact, is very useful, very straightforward to handle if the source term has exponential decay. Okay, if the source term does not have exponential decay, you can rewrite this OS into this form with the differential structure, and then plus this has strong decay, but does not have the this good structure. Okay, so you can decompose the OS NS in these two operators. Okay, so if the source term either has decay or differential structure, then you can first solve the case with decay, and then solve the OSS with the source term FS. But you have an error. You have to recover this LD phi1 by using the original OS. So in fact, if you only look at the OS for incompressible NS, you can do it in 3 steps to find the solution with Navier boundary condition. Okay, but for MHD is more complicated. Okay, MHD, the OS system cannot be used to estimate even the source term has strong decay. So we need to decompose into OSS plus LD and OSD LS. Okay, AS means a differential structure, some elliptic structure. D means strong decay, like e to the minus y, or constant times y. Okay. So so with this decomposition, then if we can show that OS can be used to estimate when the source term has differential structure, and OSD can be used to handle the fast decay, then we can iterate, okay, to find the solution. So this is the basic idea. So if the source term has strong decay, so we how to solve this OS system? So we first step, replace OS by OSD. Then in the next step, we have to recover LS zeta naught, okay, by using OSS. But in OSS, there's an extra error term, LD Z0. So we need to use the OSD to recover this one. Okay, so this is the second step. Then you can continue, then end up with this series. So if you plug this series in the original OS system, then you have the error term. In addition to the source term F, you have this error term. Okay, so now if this series convergence is convergent, then this is 0. Okay, eventually, when capital N goes to 0. So you solve this series is the solution we are looking for. So if the source term is a differential structure, then we start with the OSS first. And then in the second step, you have the error term, fast decay, then you can repeat the above process to find the solution. Okay, so this is the idea, and in reality, then we need to define OSD is in this form. Okay, basically keep the classical OS structure, and the OSS is in this form. Okay, keep the differential structure. Okay, and then you iterate and estimate, then you can show that this in fact can be solved. Okay, because I don't have time to so again, the low slip boundary condition can be obtained by apply the Rose film again. Okay, so a simple remark on other beta, parameter beta. So for other beta in this interval, then the fast mode cannot be used the area function anymore, but you can construct it by some iteration. Okay, and for beta in this region, then we can do the same thing, but for this smaller region interval, then one need to construct the slow mode in one order higher in alpha. Okay, so this is syntetical. So in the remaining time, I would like to talk about the compressible NS, which is closer to kinetic. Okay, in some sense. Okay, so again, let's first look at the isentropic case. Okay, so this is the 2D compressible NS. We have the density, velocity, pressure, depends only on the density. So now we know that if you look at the Pendle type layer, the pressure does not have a layer. So that means the density does not have layer in the leading term. So the shear background profile can be chosen like this. The density is just a constant. Okay, no layer. But the velocity has a layer. The tangential velocity is a function y over square root epsilon. And the normal velocity component is chosen to be 0. Okay. Again, we look for this solution. Okay, this type of solution. But now we don't have any stream function, right? Because it's compressible case. We don't have divergence free. So we have low UV free functions depends on y times this eigenmode. So we plug this into this system. Oh, okay, sorry. So this is the technical structure assumption on the background flow. Basically, this is the most important one. So what we can handle is the case when the Mach number less than 1. Okay, so in the subsonic case. So for the transonic case, I think this is extremely difficult. So this assumption, M is the Mach number. Okay, so this assumption if you look at the case when m equals to 0, just corresponds to some concave assumption on the velocity field. Okay. So this is the film the result I obtained with Zhu Zhang, okay, recently. So we can show that there is a constant m naught. So far, what we can show is this m naught is square root 3/3. But this obviously is not optimal. We're trying to push it closer to 1. Okay. So this is m naught. So if the Mach number less than m naught, then basically the statement I just mentioned holds. Okay. So when alpha equals to epsilon to this power, you have this type of solution corresponds the corresponding parameter satisfies this condition. Okay, so this leads to again the instability. Okay. Okay, so how to do this? Okay, so the new idea in the proof has 2 parts. Okay, the first part is that the classical OS equation is derived from the incompressible flow. Okay, but here we can also derive an equation. We call it the OS equation for the compressible NS. Okay, so it has a similar structure but more complicated. And there's another iteration scheme we would like to introduce. The first one is approximation is we call it the quasi-Stokes approximation, and the second is the quasi-compressible approximation. Intuitively, in the quasi-compressible approximation, it means we drop the part of the compressible term, okay, to make it almost like incompressible flow operator. For the quasi-Stokes equation, we drop some convection term in order to make the operator has some elliptic structure. Okay, so this is the idea. So if you do this, then this intuitively you write the linearized NS system into again these 4 operators. Okay, one is quasi-Stokes past fast decay and quasi-compressible with elliptic structure. Okay, then once you have this decomposition, then we can again iterate. Okay, so in mathematics, okay, so in formula, I just put it down. So the linearized operator for the compressible NS is these 3 equations. Okay, conservation law and momentum for 2 velocity components. Okay, they are coupled together. So so now, for example, if you this theta is just the divergence. For example, if you solve the first equation for u and pi into the second equation, right, and then it is more complicated. However, if you solve the first equation, u in terms of v and rho, you drop the rho and pi into the second equation, it gives you some simple structure because rho corresponds to the compressibility of the fluid. Okay, and v here somehow related to the incompressibility. Okay, so precisely what this means is that if in the second equation, if you add this extra term and drop the divergent terms, okay, then we call this system as quasi-compressible approximation. Now this system, in fact, can be written very elegantly, okay, because you can solve the first equation for u and pi in the second equation, and then solve the second equation for rho and part of the last equation. Then you can end up with this this equation. we call this equation as the OS equation for the compressible NS. Okay. So now this involves operator lambda. Okay. So lambda is this operator, and A is just a function. A is 1 minus Mach number square times this square. Okay. So so if Mach number is 0, corresponds to the incompressible case, A is 1. Okay, so A is 1. This is exactly the classical OS. Okay, but for compressible case, this A is a complex function. Okay, depends strongly on M and C. Okay, so this is the main difference. So for the quasi-strokes, okay, so you keep the elliptic structure and drop the fast decay term, this term, okay, in the second equation, okay. Then this equation can also be solved, okay. So you can iterate and then find the solution to the NS, and then prove a similar result, okay. So finally, I would like to make 2 comments. The first comment is the full compressible NS, because here we didn't consider the temperature. Okay, so if temperature is involved, then the case is much more complicated. In physics, the temperature also has some stabilizing effect in analysis, because we only know the pressure has no layer in the first order. So if you have temperature, heat transfer, then both the density and the temperature has a layer. Okay, so this is very complicated, and so far we don't know how to handle. Okay, but I think if the temperature is around a constant, okay, fixed constant, we still keep the subsonic assumption, and this can be done, but the calculation is very involved. So finally, I would like to comment the Boltzmann equation. So we all know that the Boltzmann equation, if you impose the diffusive boundary condition, the Coulson number is close to 0, then the Fourier part can be approximated by the compressible NS. Okay, so now for the compressible NS, we have the solution profile I just mentioned with some going mode. So maybe for the Boltzmann equation, we can also construct some solution with similar structure. Okay, so this is, I don't know, just some feeling. Okay, I haven't formulated the problem yet. Okay, so thank you.
Thank you, Tong, for the nice talk. Thank you. So yeah, so the floor is open for questions. So Michele, I see that you might have a question.
Okay.
Yeah, I would have a question. Thanks for the talk. It was very nice. Like for the compressible system, if you assume that you have no shear viscosity, then maybe it's like when you have MHD, you assume that you have no dissipation in the magnetic field. If you assume that you have no shear viscosity and your background flow is the wet flow, then you have like the conservation of the vorticity plus the density, which is somewhat the linear analog of the conservation of the potential vorticity. Have you considered to study the problem where you have no shear viscosity? It should be somewhat maybe simpler to analyze, or?
Yes, this is a very good point. I haven't thought about this in this setting, because yes, I don't know. I cannot give you an answer, but this is a very interesting problem to look at.
Okay.
Yes.
Thanks.
Is there any other question, comment? If not, let's thank Tong again.
Okay, thank you.
Thank you very much. And let me see.
So I stop sharing.
Yes.